Gnanam paramam dheyam. Knowledge is supreme.
Today's discussion is going to be a recapitulation for almost all of us, I think. So, now for the rest of this course, we are going to discuss NMR spectroscopy, except maybe for the last class. Now, everybody knows what NMR stands for, nuclear magnetic resonance, and in chemistry courses, of course, you have come across NMR data and all in different courses, and even beyond chemistry, you know that when we have a soft tissue injury, what we do is we go and get MRI image many times. Okay, so, it is a very useful technique. Several Nobel Prizes have come out of this field of study, and it is a great boon to chemists, because as we have discussed sometime towards the beginning of the course, the problem with being a chemist at one point of time was that you make some new compound after a lot of toil, and then you spend 1 year to find out what it is by wet chemistry, if you have to do it by wet chemistry. So, the kind of experiments you have perhaps done in your undergraduate days, you want to find out what the functional group is by doing the diazo test, ring test, right, esterification and so on and so forth. So, if you have to do that, first of all you spend this compound that you have made with so much of effort, and secondly it takes a lot of time and everything is indirect anyway. So, that was not such a happy situation. Things changed drastically because of the advent of spectroscopy, and as we have discussed in IR spectroscopy, we can actually tell which functional group it is without having to do a reaction. But then even IR is not enough. The one spectroscopic technique that has made the life of chemists much easier is NMR spectroscopy. You do an NMR spectrum, you get an NMR spectrum, you understand which compound you have been able to make, and that is what everybody does all the time. Okay. So, very often the chemists are actually accused of practicing palmistry using all these spectroscopic techniques. If you put it in more polite terms than palmistry, we can say it is pattern matching. So, see whether how many lines are there and where, what is the chemical shift, whether it is a doublet or a triplet and so on and so forth, you can figure out which compound it is. So, the other common allegation against chemists is that chemists pretend as if they can see molecules. Well, actually we can see molecules through this spectrum. But in this course, we are not going to learn how to identify molecules using NMR spectroscopy. In fact, I am quite bad at interpretative NMR spectroscopy. That is what almost all of you will learn next semester in CH 521 formally. You might have done some in other organic inorganic courses. In the next couple of weeks in this course, we are going to try to understand how NMR spectroscopy works, alright, and we are going to talk about one NMR spectrum by and large, and that spectrum is displayed right in front of you, the NMR spectrum of alcohol. That is all that we will do in this course, but we will try to understand why this NMR spectrum looks like what it does. So, what we are now doing is, if we look back at what we have done in this course, we are trying to understand how light interacts with matter, and when you talk about light interacting with matter, you know very well that according to energies, light can be classified in many ways, and electromagnetic spectrum actually spreads from very high energy to very low energy. We have not really talked about anything to do with gamma rays and all, but we have talked about the kind of spectroscopy that uses ultraviolet, visible and X-rays. What kind of spectroscopy is that? UV-Vis and X-rays? Okay. UV-Vis spectroscopy uses UV-Vis spectroscopy, UV-Vis spectrum. What kind of an answer is that? So, say something else, that is obvious. So, using UV-Vis electronic spectroscopy. We get to learn about electronic levels, and that is what we have been doing immediately before. Okay. Then using IR, what is the information that you get about molecules? Vibrations. Okay. And using microwave, what is the rotation? Now, we have almost covered the entire electromagnetic spectrum except for gamma rays and all, right. So, what we will do for the rest of the course is that we will talk about radio frequency, and what do radio frequencies tell us about? In radio frequencies are used, so radio frequency you understand there are very small energies are there, right, smaller than rotation. So, radio frequencies are typically, they have the energy that are associated with what we will call spin resonance. We are familiar with spin in some way or the other, right. So, when we have spin flipping alpha to beta, beta to alpha and so on and so forth, that is the kind of energy that is involved falls in the radio frequency regime. Okay. Of course, it is a different kind of spectroscopy than what we have been doing so far. Why? Because see, these rotational levels and all, they are already there in the molecule. Not so in case of NMR. As we are going to discuss later, the way you make the energies of alpha and beta spins different is by applying a magnetic field. In absence of magnetic field, alpha and beta spins have the same energy. So, if the same energy, there is no spectroscopy. Okay. So, first you have to apply a magnetic field, right. You are really being cruel to the molecule, aren't you? The molecule is happy with all spins with the same energy and all. You apply a magnetic field from outside, disturb the molecule, create division between two kinds of spins. It is a really divisive kind of spectroscopy that you do, and then you see how much divided they are. That is essentially how NMR and ESR work. So, what we are going to use, and all this is perhaps known to you, it is almost common knowledge now, common sense, right. So, the thing is, not all nuclei actually absorb radio frequency even if you place them in magnetic field. See, to start the discussion, we have to start from a point that is very simple, right. So, right now we are not even talking atoms or molecules or anything, we are talking about nuclei. You can even think we are talking about isolated spins, okay, different kinds of isolated spins. So, it is not necessary that all nuclei will absorb radio frequency even if you apply magnetic field. What kind of nuclei will absorb? Kajal, little louder. What is not equal to 0? That is right. Spin not equal to 0. What is spin? When we say spin not equal to 0, spin number not equal to 0, what is that spin number I? What kind of number is it? It is a quantum number, you are right. It is a spin quantum number. That is what you said, right? So, the nuclei are associated with spin quantum number. So, the spin quantum number has to be non-zero. And how to determine spin quantum number, that is a little long story. To just give you the final result of it, this is what it is. If the atomic mass and atomic number are both even, then I is 0. If atomic mass is even and odd atomic number is there, then I is a whole integer, whole number. And if you have odd atomic mass, then you have half integral spin quantum numbers, okay, half 3/2 and so on and so forth. Some examples are given there. So, out of all these, most of the time what we do is we work with this proton. Then, since most of the time you look at organic molecules, you do a lot of 13C NMR as well. If you are an inorganic chemist, especially main group inorganic chemist, then you might be interested in this phosphorus NMR. 31P, 59 is also not very uncommon. So, different kinds of nuclei can be interrogated. Now, the question is, how do you know, how do you interrogate proton selectively or 13C selectively? That is what we will discuss slowly. So, but before that, just for the record, it is a quantum number, let us not forget. And what kind of a quantum number is it? We are familiar with the spin quantum number of electron, right. What is it? What is the spin quantum number of electron? Half or plus half and minus half? No. it is half. What is plus half and minus half? It is ms, right? Spin magnetic quantum number is plus half and minus. Please do not forget this. S is only half. Okay. And what does that S give us in case of electron? It gives us the spin angular momentum, right? Or if you go back even further, if you think of L in case of hydrogen atom, right, azimuthal quantum number, what does it give us? The total angular momentum, square root of L into L plus 1 multiplied by h cross. In case of electron spin, it is square root of S into S plus 1 multiplied by h cross. In this case, similarly, it is square root of I into I plus 1 multiplied by h cross, right. This is the total spin. So, remember total spin means it is the length of the vector, but then even if the length of the vector is defined, it can point this way or this way or this way or this way. So, if the direction changes, the length does not change, what changes actually? I have the same arrow, but I change direction. Length will of course not change, what will change? So, as a result of changing angle, which property of the angular momentum changes? Z component of angular momentum, right. If it is like this, then it is large. As the angle changes, this goes down and here it is 0. If it goes down, then it goes down in this way, okay. Z component of angular momentum. So, Z component of angular momentum, you will remember, is determined by the magnetic quantum number. In this case also, you have magnetic quantum number, that is, we just write m for now, sometimes you write mi or ms. So, Z component of angular momentum is given by m into h cross, and as usual m goes from plus I to minus I. So, 2I plus 1 values, okay. So, the treatment is very similar to this angular momentum that we have done in case of electronic orbits or even for spin. So, for proton, the spin, what is the spin for proton? I think you know this. Spin for proton, spin quantum number for proton, half. So, what are the values of m for proton? Plus half and minus half. So, you have something pointing upwards, that is one possibility, or you can have it pointing downwards, that is another possibility. Can it be like this? Can it be like this or this? No, right? There has to be an angle. Why? What is the length? What is the length of the arrow? Spin quantum number is half. So, the length of the arrow is square root of half into half plus 1, 3 by 2. So, what will it be? Root 3 by 2 h cross. And what is the z component? Z component is h cross by 2, isn't it? Right. So, if this side is h cross by 2, this side is root 3 by 2 h cross, you can understand that the angle can never be 0, right. There has to be some angle, and you can work out what the angle is from the sine or cos values, some well defined angle. So, what angle is this? Theta, right. Angle with z axis is theta. What is the phi value? Phi value is not defined. This is important to remember. Very soon we will start drawing cones. The reason why we draw cones all the time is that for this spin, theta is well defined because you have a specific value of m and a specific value of I. Phi is not defined. So, you can think that this is delocalized all over the cone for which a particular theta value is defined. Alright. So, now we have the spin, fine. What happens when you apply a magnetic field? Of course, we are going to do a proper quantum mechanical treatment of this next week. And when you do a proper quantum mechanical treatment, we will talk about the interaction, we will have to write the Hamiltonian and so on and so forth. But if we, for today, if we take a little easier approach, then this is what we can think. For a magnetic field B0, if mu is the magnetic moment that is associated with the nucleus, that magnetic moment classically is given by gamma into I, where gamma, I think you know, is magnetogyric ratio or gyromagnetic ratio, both terms are used. It is given by Gi into mu n. Mu n is your nuclear magneton. Are you familiar with the term Bohr magneton? You learnt it in context of hydrogen atom perhaps. This here is the nuclear equivalent, nuclear magneton, which has some specific very small value. Okay. So, the interaction energy is given by E equal to minus mu into B0. not very difficult to understand. You can even intuitively you can perhaps accept this result minus mu into B0, and then if you consider the field to be along z direction, of course, field will be along a particular direction, and the convention is you define that direction to be z. So, you can write it in terms of z. Now, what will be important really is the z component of the nuclear magnetic moment, right, mu z. So, if the field is along z direction, then you write mu z is gamma I z. So, E will be minus mu z into B0, extrapolating from here, that will be minus gamma m h cross B0. Okay. Now, you see, if I apply a magnetic field, now what happens? What are the possible values of m for a nucleus, for a proton? Plus half and minus half. M is plus half and minus half, do not forget, right. So, if it is plus half, what is the energy of interaction? This m is half. So, half minus half multiplied by gamma h cross B0, and if m is minus half, then what will it be? Same, but with a plus sign. So, minus and plus, what is the difference? Energy minus means lower energy or higher energy? Lower energy stabilization. Energy plus means higher energy. So, you can think of a situation like this, but before that, well, this is just a prelude of what will happen next week. So, now that you know this term, you know very well how we formulate quantum mechanical problems. We think of the classical mechanical interactions as far as possible, and from there we try to construct the contributions to Hamiltonian. That is what we will do next week using this Hamiltonian. But for now, you can think like this: when the field is off, is there any energy of interaction? Of course not. If there is no field, what will the nucleus interact with? So, both alpha and beta have the same energy. Here we are showing, say, proton or 13C. Now, when the field turns on, you have told me that the alpha spin, that is stabilized and the beta spin is destabilized. So, this is the situation. All these figures that we use today are from Atkins textbook. So, you can study this part from Atkins or from Banwell, does not matter, it is quite easy. Next part you can study from Macquarie and Simon, or I will tell you another book. Okay. So, this is what happens: alpha spin is stabilized, beta spin is destabilized, and the magnitudes are in both cases half gamma h cross B0. So, the difference of course becomes gamma h cross B0. Now, it is not at all difficult to see that this difference depends on the magnitude of the field you use. If B0 increases, then the splitting is also more, right. The separation between energies of alpha and beta spins is also more. Okay. So, this is where it is different from what we have been studying so far. For say vibrational spectroscopy or rotational spectroscopy, the energy gaps are intrinsic properties of the molecules or atoms that you study. Of course, I mean, if you say atoms, how will it rotate or vibrate? Molecules that you study. But in this case, the energy gap that you have is very much a function of the field that you use, and that allows us to change the resolution of our experiment. As you understand, more splitting means better resolution. Do you agree with me? Is it easier to measure 1 micron or 1 foot? 1 foot, right? So, if you can make the separation bigger, it is easier to measure. Of course, there is a limit to it. It is easier to measure 1 foot than the distance between Earth and what is the star that has been found very recently, earlier this week. Let us see who can answer this question. Icarus. That star has been named Icarus. Of course, I leave it to you to study the story of Icarus, why it is called Icarus, what, so but that you can study. But of course, it is not so easy to measure that distance. So, there is always some compromise value somewhere. So, greater B0 means bigger splitting and therefore better resolution. We will dwell upon this point a little later again. But for now, you can say that now, if I bring in light whose energy is equal to gamma h cross B0, then I have resonance, Bohr resonance condition is satisfied. So, this is your Bohr resonance condition. equal to gamma nu L, when nu L is the frequency of light that you are using, and typically this would be in radio frequency regime. Okay. The kind of magnetic fields that are used, if you use too big a magnetic field, then actually some other effects come in. So, you do not want to do that. So, the splitting that you typically induce is in microwave regime. So, you can use microwave to probe it. So, once again this is somewhat like a pump probe experiment, is it not? We have discussed pump probe earlier. You use a pump to excite the create an excited state population, and then you use a probe to investigate it. In this case also it is a little different. You are actually creating the excited state itself by using the magnetic field, and then you use the light to probe the differences. Alright. Now, the reason why we write nu L, okay, we will come to that, but here your typical value, if you use a magnetic field of 12 Tesla, is 12 Tesla a large magnetic field or a small magnetic field? So, okay, let us put things in perspective. You have seen bar magnets, how many Tesla is that? Small bar magnets, yes, maybe even less than that. 12 Tesla, well, you can work with bigger magnetic fields as well, but 12 Tesla is not very small. See, sometimes you read of accidents in MRI machines, right? Somebody entered with a gas cylinder and immediately got sucked into the machine and somebody died, right, last month or something. So, it is not too small a magnetic field. 12 Tesla is definitely not too small a magnetic field. That is why if you have a pacemaker and all, you are asked not to go near. When we enter NMR lab, we are asked to discard all metallic object, and if you have say some operation by which some screw or plate has been inserted in your body, you better stay away from NMR machine. It is not too small a field. So, if you use 12 Tesla, then this frequency is 500 megahertz for protons. What will it be determined by? It will be determined by not only B0, but also gamma, the magnetogyric ratio. So, for protons it is 500 megahertz. Now, those of you who are a little familiar with NMR spectroscopy would know that in our department we have an NMR machine, do not we? How many megahertz machine is that? 600 is there in SAIF, not in our department. In our department we have a 500 megahertz machine. It is huge, right? Huge. Actually, what is huge is the Dewar, but then the magnet inside is also huge. So, the reason why our machine in the department is called a 500 megahertz machine is this. The magnet inside that machine is a 12 Tesla magnet, right. Then of course, you can figure out what is the how big the magnetic what is the magnetic field strength of the machine in your SAIF. In SAIF you have a 600 megahertz machine. From these values, can you not calculate what is the magnetic field of that machine? It is directly proportional, isn't it? It is directly proportional to B0. So, if 500 megahertz corresponds to 12 Tesla, 600 megahertz corresponds to how much? 12 multiplied by 6 divided by 5, okay, you can do the math. So, 900, we also have a 750 megahertz machine in the same building as SAIF, CRNTS, that you can calculate what is the magnetic field of that magnet there, okay. So, basically the bigger this megahertz value is, bigger is the magnet, stronger is the magnet, let me say, okay. That is all that is there. Why do you want to use a stronger magnet? Because you get a greater splitting, and even intuitively we have said that a bigger splitting is better. So, as we go further in this discussion, we will understand in a little more detail why it is better to get a greater splitting. It will come slowly. But for now, do not forget, we are talking about the isolated proton, the physics, not so interesting so far, not chemistry yet. When it becomes chemistry, then it is interesting, right, Shravana? All right. Now, but before we go there, one thing that I should say is that nu L, that L is not for light, L is for Larmor, Larmor. It is called the Larmor precessional frequency. Now, see, the thing is this, when we discuss NMR, the right thing to do is to use quantum mechanics and proceed accordingly. Fortunately for us, you can understand what is going on even without using quantum mechanics. The classical model can give you at least qualitatively a more or less correct picture. And the classical model is, if you have this kind of an angular momentum in a magnetic field, what kind of a motion do you expect? You expect a precessional motion. Okay. I will not work it out here because it is too simple. If you read this portion from Banwell's book, you will see the frequency of this precessional motion has been worked out, and the expression for this, what is called Larmor precession frequency, comes out to be the same. So, that is something that is kind of amusing. The frequency of precession of the angular momentum around the applied field axis is exactly the same as the frequency of light required for a transition from alpha spin to beta spin. Okay? It is just like that. What can we do about it? But so, this is your homework. Please read this portion about precessional frequency, either from Atkins' book or from Banwell's book. Right. But as I said, all that was dry physics so far. Now, it becomes interesting when you think of its applications in chemistry, right? What is the Hindi for chemistry? Hindi word for chemistry? Rasayan, right? Yeah. So, there may be some other version, I do not know, but then the Ras comes only when you enter Rasayan. So, the reason why it becomes so interesting for chemists is that if you now move from bare nuclei to nuclei inside molecules, then something interesting happens. Now, see, when it is inside molecules, you can think that you have this nuclei enveloped by charge cloud provided by electrons, right. So, one extreme is no charge cloud. So, you have something. If you have a charge cloud, then what happens? Then charge cloud itself, there some magnetic, reaction magnetic field will be generated when you apply a magnetic field, right. That is going to, well, as a first approximation, that is going to sort of shield the nucleus to some extent from the magnetic field that has been applied, right. So, this is like survival instinct of the molecule. You apply a magnetic field, immediately the electrons that are there set up a magnetic field which is opposite in direction. That is, of course, physics, right. So, but then the thing is, in a molecule, if you think of different nuclei, they are in different chemical environments, which translates as they are surrounded by different amounts of charge density. So, this shielding part that is there is different for different nuclei in different chemical environments. As a result, what you get is, you get something called chemical shift. So, what are we saying? We are saying that the effective magnetic field felt by the nucleus is something like this, B0 multiplied by 1 minus sigma, where sigma is the shielding constant. It depends on how much of electron is there around that particular nucleus. And even in the same molecule, different nuclei will experience different amounts of electron charge cloud around them, and therefore, will have different values of sigma, shielding constant, right. So, what happens is, if you now instead of B0, if you write B effective in the expression for Larmor frequency, this is what you get. Larmor frequency is 1 minus sigma multiplied by gamma B0 divided by 2 pi. Now, suppose you focus on one kind of molecules, one kind of nucleus, sorry, protons. You use a 12 Tesla magnetic field. What is the expected Larmor frequency? 500 megahertz, okay. But then, if you have 3 kinds of protons, let us say, go back to the only example that we will be using, alcohol, CH3, CH2, OH. So, OH proton, CH2 proton, CH3 proton, they are in different kinds of chemical environments, and they will have different sigma values, and therefore, nu L will also be different. right. So, that is what it is. If you look at a low resolution NMR spectrum of alcohol, then you actually expect 3 different lines at 3 different Larmor frequencies, depending on what kind of chemical environment each kind of proton is in. Okay. Now, why CH3 protons are in high field, why OH protons are in low field, let us not even worry about that at the moment. That is not very difficult to understand. But the point to understand here is that you should have 3 different kinds of Larmor frequencies. Of course, the problem here is that if you want to work with these frequencies or this, then the issue is, we just said that the frequencies are dependent on the magnetic field that you use. Okay. So, instead of a 12 Tesla magnetic field, if I use 16 Tesla, what will happen? The Larmor frequencies will all change, right. And in fact, a 12 Tesla magnet that we have here and a 12 Tesla magnet that we might have in Pune, actually 12 is never 12, right, there is always a tolerance. So, even between 2 machines, there will be a variation of spectra, that is not a happy situation. Okay. When I get a spectrum, I do not want to say that this is recorded on a Bruker machine situated in IIT Bombay chemistry department, this is the latitude, this is the longitude, this is the time of measurement. But actually even on the same machine, if you measure now and 5 years later, your frequencies will be different, because magnetic field is not something that does not change over time. So, there must be some way in which we can find a way of defining these chemical shifts sigma without being dependent on the magnetic field that we have used. That is why instead of sigma, we use this delta scale. Okay. What is delta scale? We have already said these two. Delta scale is defined like this. So, what you do is, if you want to eliminate the dependence on the instrument, then the best way to go about it is to wake up and to use a reference. Okay. So, what you do is, you do back to back measurements. You use some reference, let us say nu for the reference is nu 0, and let us say nu for your sample is nu, then delta is defined by nu minus nu 0 by nu 0. We could have actually stopped there, but then that comes out to something like 10 to the power minus 6, okay, because nu minus nu 0 compared to nu 0 is small. So, it is for good measure multiplied by 10 to the power 6, and the unit is given as parts per million, ppm. So, when that happens, you put in the values of these nu and nu 0, you get 1 minus sigma multiplied by B 0 minus 1 minus sigma 0 multiplied by B 0 divided by 1 minus sigma 0 multiplied by B 0. Okay. Even without simplifying this any further, you can see that B 0 cancels in this expression, right. There is 1 B 0 in the numerator, 1 B 0 in the denominator, they just cancel off. So, you are left with something like, I do not know why I did not write the next step, but bear with me. So, we are left with something like sigma 0 minus sigma divided by 1 minus sigma 0, alright. So, this is your delta scale. The good thing about delta is that delta on one hand is field independent. It does not matter whether you make the measurement here or in Kamskatka, you get the same value of delta always, and on the other hand delta is proportional to sigma. So, it gives you the same information, and as most of us would know, the most commonly used reference is your tetramethylsilane, and there are reasons why you use tetramethylsilane. Great. So, these are the characteristic rate shifts. As I said, the figures are, yes, Shushnata. Once the magnetic field has been applied, so if you remember, when you have this kind of a charge cloud, you apply the magnetic field, right, then what happens is this reaction field is set up, right. You can think classically of this charge cloud in motion, right. The resultant magnetic field that you get from there is always opposing to the magnetic field that you employ, isn't it? This is something that you must have studied in this electricity and magnetism in 11, 12. Yes, so you think of it as charged particle in motion. Magnetic field is constant, electron is not. Huh? Electron is moving, right? So classical picture is it's moving in orbit. Okay, fine. But what I am trying to say is that even if the B0 is same, what he's saying is that you fix the magnetic field. So if you think of the big magnetic field, think of the lines of force, they are all the same. That's what you are trying to say, isn't it? No, I mean I thought the moment you apply a magnetic field, the opposing field is set up, right? I don't see a problem with that. No, no, no. Let's discuss that later. No, when you have a constant magnetic field, then also you do get the opposing field. We'll discuss it offline. Alright, so these are the characteristic chemical shifts and these are the characteristic chemicals. Well, that one was for proton, this is for 13C NMR. Now, so one kind of this opposing field that becomes very important is when you have aromatic systems, because this pi electron cloud is more loosely held. So, ring currents can actually give you a greater shielding, and this is an example that perhaps many of us would know already. Here in the same molecule you have protons that are shielded and you have protons that are de-shielded, but because of the same field. So, what we have shown here is this is the direction of the applied magnetic field and these are the lines of force of the reaction field. Okay. Now, see, think of this proton. What is the situation in this proton and what is the situation in this proton? If you think of this proton, you see the applied field is upward and the lines of force of the reaction field are downwards. So, this proton is actually shielded. The effective field at this proton is less than the applied magnetic field. But if you think of this one, here we have something funny. We have an applied magnetic field, lines of force of the reaction field are also pointing upwards. So, here in this case actually the reaction field reinforces the applied field for this proton. So, this proton here is going to get de-shielded. Okay, this is what same is true for this one, does not matter. And this kind of shielding and de-shielding in case of aromatic rings is not restricted to protons that are covalently attached to the ring. Even if you use a solvent like benzene, then you can see this strong shielding and de-shielding effects of solute molecules. Of course, these are transient effects. So, interpreting the data is a little more involved than what I might have given the impression of right now. Okay. So, this here is an actual spectrum, NMR spectrum of ethanol. So, what do we see? What do we expect? We expect 3 groups of lines. We have 3 groups of lines and then we expect the intensities to be proportional to abundance. So, the way that is done in NMR spectroscopy is that as you see none of these lines, and as we have learnt earlier also, a spectral line is never like a delta function, right? There is always a width. So, if you want to talk about abundance, what you need to do is you need to work out the area under the curve, integrate. So, when you integrate, this is how the data is typically shown. This here you go from here to here, this is 0, this is the length of this sigmoid kind of curve is proportional to the area under the curve, and you can see that this is to this is to this is about 1:2:3. That gives you the number of protons contributing to each of these groups of lines. So, see the area under the curve gives you relative abundance. So, since the area under this curve is such large compared to this one, from here we can see that these lines must be for CH3 protons. This one is more than this, double of this. So, these must be for CH2 protons, this must be for the OH proton. Okay. But the question that arises is why is it that we do not have nice single lines? Why do we have so much of fine structure? And the answer to that is that there is coupling between different kinds of protons. What is the meaning of coupling? Okay, think of a magnet that is suspended. One of the classical experiments that you might have even done yourself when you were in school. Take a bar magnet and suspend it using a string. What happens? It orients itself in the north-south direction. Okay? That is because that is the direction of Earth's magnetic field, and that is what causes the preferential orientation. Now, if you bring another magnet near it, does not the orientation change? Why does it change? Because of the magnetic field of the second magnet you have brought near it. So, the analogy with NMR is that you can think the Earth's magnetic field is analogous to that 12 Tesla, 15 Tesla magnetic field that you are using in the NMR machine, and the nuclei are like the small bar magnets. Since they are close to each other, they will also orient each other's energy. That they will also determine each other's energy to some extent, which will be a secondary effect. This is called coupling in a very qualitative manner. We will do a little more detailed quantum mechanical treatment of this spin-spin coupling next week. But we can do it at least qualitatively, because it can be done qualitatively without much hassle. So, if you think of a two spin system, okay, I have two protons, okay, and we are considering two protons with different chemical shifts. This is called an AX system. Are you familiar with this terminology? When do I say a two spin system is an AB system? When do I say that a two spin system is an AX system? Actually, it is very easy to understand. Think of the English alphabet. B is right next to A and X is very far away from A. That is what it means. If the two groups of protons, if the two protons, right now not groups, if the two protons have chemical shifts that are different but not very different, close to each other, then that is an AB system, and if the chemical shifts are significantly different, then it is an AX system. That is all. Here we are talking about an AX system where the chemical shifts are different. As we are going to discuss at least briefly later on, there is a reason why you want to work with AX systems. If the chemical shifts are very different, then the magnitude of coupling is small compared to the chemical shifts. That is what gives us what we call first order spectra. You understand what I am saying? You have this bar magnet suspended and then it is pointing north south, right. So, and you bring in another bar magnet. If the strength of the second bar magnet is more or less same as the Earth's magnetic field, then you have a more complicated problem. But if this second bar magnet has a small magnetic field, then you can treat it as a small perturbation over and above the existing system that is there. Okay. So, if you have a large chemical shift, will coupling change? Will coupling depend upon the magnetic field that you use? No, right? Because coupling is coupling between nuclear spins. They are intrinsic properties. If you use a bigger magnetic field and cause a bigger chemical shift, then, well, when I say chemical shift, I do not mean delta, I mean sigma or nu L if that helps. So, then what happens is this effect of coupling does not get convoluted with the effect of chemical shift. We will elaborate upon this a little later. So, for now we have two systems, alpha and this A and X, right. What is the happiest situation? If you remember the expression for the energy of interaction of the magnetic field with spin, what is that expression? Magnetogyric ratio gamma multiplied by m multiplied by h cross. Is there a minus before that? There is a minus, right. So, we said that alpha spin with m plus half is stabilized, beta spin with minus half gets destabilized. So, now we have a two spin system. If both have upspin, both are alpha, then both will be stabilized, that is the least energy situation. So, the lowest energy situation is this will be the energy minus half, the way it is written here, h nu A minus half h nu x. This is the alpha A alpha x situation, both are upspin. What is the diametrically opposite situation when both are beta? Both will be destabilized, and what is the energy then? Now it is plus half h nu A plus half h nu x, beta A beta x. What are the two intermediate ones? One is up, one is down. Okay, one is up, one is down. So then these are two alpha A beta x and beta A alpha x, and this is the situation that we have in absence of any coupling. Okay, only external magnetic field is there. Now let us bring in coupling as a perturbation. So even intuitively we can say that the energy of coupling is going to depend on both the spin quantum numbers, right, on both the spins. Do you agree with that? The coupling energy is given as E equal to J into I1 into I2, right, because if I1 is 0 or I2 equal to 0, then there is no coupling anyway. So this J is called the coupling constant. Coupling constant is something that, as we will see, we can determine experimentally, but you can also find out the value of coupling constant theoretically. That is what people like Professor Rajaraman do many times. Theoretically, you can actually arrive at the expected coupling constant values. So if this is the case, now see in what will happen now. When I say I1, I2, I have to consider the m values. When both the m values are plus half, then what will happen? Stabilization or destabilization? Destabilization, half into half, 1/4. So it will be 1/4 multiplied by j, destabilization by that amount. What happens when both are minus? Again destabilization by 1/4 of j. What happens when one is plus, one is minus? We have stabilization by 1/4 of j. That is how you get this one. When you have alpha alpha or beta beta, you get destabilization. When you have alpha beta kind of situation, you get stabilization. Of course, one thing we have completely neglected here is, but it is this is Ax, that is okay. So now what will happen? Let us see what each transition stands for. Suppose you go from here to here, alpha A alpha x, alpha A alpha x to alpha A beta x. What has happened? Alpha A has remained alpha A. For the nucleus x, there has been a spin flip from alpha to beta, right. So what is this transition? Is this transition for A or x or both? Alpha A alpha x to alpha A beta x is a spin flipping transition for A or x or both. X, because alpha A is still alpha A, alpha x has become beta x. So going from the first level to second level is really a spin flipping only for x, not for A, and that is evident in the energies as well. What is the energy of transition? Subtract this from this, minus half h nu A minus half h nu A, that cancels, half h nu x minus half h nu x, that is how much? Yes. So this energy gap is h nu x. So in absence of coupling, this transition gives you a line at nu x, the characteristic Larmor frequency of nucleus x. Alright. What happens if you go from alpha A alpha x to beta A alpha x? Alpha A alpha x to beta A alpha x. Is it a spin flip for A or x or both? A and not x. Clear? And you can again work out that the energy in that case is nu A, frequency is nu A. Okay. So in the unperturbed situation, when there is no coupling, this is what you should get. you get a line at nu A, you get another line at nu x. Alright. What happens when you go from, okay, can you go from alpha A alpha x to beta A beta x? If you could, what kind of a transition would it be? Alpha A alpha x to beta A beta x. That means A has undergone spin flip from alpha to beta, x has also undergone a spin flip from alpha to beta, right? Can that happen? Can I do it in one transition? We cannot, because that would violate what we call one photon rule. Did we talk about one photon rule earlier in this course? Okay. What did we say at that time? That our photons are not like Rajnikant's bullet, right? One photon is one packet of energy. It cannot suddenly split and then cause one transition here and one transition there, okay. Since photons are not Rajnikant's bullets, we cannot have alpha A alpha x to beta A beta x transition. Are we clear? But what about these? Can I go from alpha A beta x to beta A beta x? Yes. So, what is it? Alpha A beta x to beta A beta x? Which nucleus undergoes a flipping? A and not x. And beta A alpha x to beta A beta x? X. What are the energy differences? Alpha A beta x to beta A beta x. What is the energy difference? Yes. H nu A or x? There are only two options. H nu A, right? Alpha A beta x to beta A beta x. Half H nu A minus half H nu A, that is H nu A, and you have half H nu x minus half H nu x, that cancels. See, it is A that is undergoing spin flipping. So, energy has to be corresponding to the Larmor frequency of A and not x. Okay. So, even for this transition you expect the line at nu A, nowhere else, and for this one you expect a line at nu x, nowhere else. Are we clear? So, if there were no coupling, then you expect two lines precisely at nu A and nu x. But now coupling has taken place. Now what happens? So, as we agreed, energy of alpha A alpha x has been increased by Hj divided by 4. Energy of this alpha betas have been decreased by 1/4 Hj. Energy of beta beta has been increased by 1/4 Hj. Okay. Now try to do it once again. Now when we go from here to here, what kind of transition is it? Alpha A alpha x to alpha A beta x. Which nucleus undergoes a spin flip, A or x? X. So this is your energy of one of the spin flips of x. Of course, this diagram is very highly exaggerated. The stabilization, destabilization are not this much, but then if you draw it to scale you won't even see it perhaps. So now this energy, you agree, is the energy for transition of x, right? What is this energy? This whole thing was h nu x. That has now gone down by 2 into 1/4 Hj, that is half Hj, is that right? This energy gap, what is it? H nu x. What is this energy gap? H nu x minus half Hj. So now for that transition we will not get a line at nu x. Where will we get the line? Somewhere here, and what will be this separation? Half j by 2, isn't it? H is gone because I am plotting nu and not energy, alright. So you do not get a line here for that transition, you get a line at a little lower energy, lower by j by 2. Now what is the other x transition from here to here? This one is beta A alpha x, this is beta A beta x. So when you go from here to here, once again there is a spin flip of x that takes place. Once again this energy gap is h nu x. What is this energy gap? This time it is larger, isn't it? It is larger by the same amount. So once again for that transition also you are not going to get a line here anymore. Just make it dashed. Rather, you are going to get a line which is higher in energy and the difference in frequency is j by 2. So, instead of a single line at nu x, you get two lines at nu minus j by 2 and nu plus j by 2. What is the separation between these two lines? J. And you can work out yourself that instead of one line at nu A, you will get a similar thing. You will once again get a doublet that is separated by j. I do not do that cat, then I will teach for 15 minutes longer. I am done, give me 1 or 2 minutes, alright. So, now see that is what gives us, what was the question? I hope we have not forgotten the question in all this. The question was, why is it that in case of ethanol, we do not get single lines at 3 different frequencies? Each line seems to comprise of more than one line except for OH. Why is that so? This is the reason. Because of coupling, you get this multiplet structure, and in fact, if you look at the spectrum, if you see by how much these lines are separated, you get a you can estimate the value of j, alright. And now you can understand, I hope, why I want a high field. Why is it that chemistry department threw away the 60 megahertz machine and bought first a 400 megahertz machine, then a 500 megahertz machine? Why is it that in SAIF and CRNTS we have 600 and 750 megahertz machine? Why is it that in TIFR they have a 900 megahertz machine? Because this separation between nu A and nu X depends on the magnetic field. This separation J does not. So, if you use a small magnetic field, nu A and nu X will be very close to each other, right? Then what will happen? If they come so close that this line crosses this and this line crosses this, then actually you get a complicated spectrum, and it is not also as simple as just lines crossing each other. There will be interaction. So, the situation is such that you cannot handle it using first order perturbation theory. You get what is called second order spectra, which are extremely difficult to interpret. That is why you want to spend more money and buy bigger magnets, so that your spectra are first order as far as possible. And of course, you know who uses that 750 megahertz machine we have inside in CRNTS? No chemist uses it, biologists, people who work on protein NMR. There of course, you understand there are hundreds and thousands of protons, chemical shifts are very close to each other. So, if you use a very large magnetic field, then only you can hope to get something that is possible to interpret, alright. So, we stop here today. Next day we come back and talk about AX2, AX3 systems and then take it from there.